Hi everyone, my name is Abbas Zaki, and today I have the pleasure of presenting my project working on optimizing the dipole and loop array for head imaging at 7 Tesla in collaboration with the UT Southwestern Advanced Imaging Research Center. So before we even begin, you might be wondering what's so special about 7 Tesla? Why not stick with the traditional 3 Tesla or 1.5 Tesla imaging systems? And so the idea is that going into the higher magnetic field strength allows us to image tissue with greater resolution. So much so that a study from the Mayo Clinic actually found that with the 7 Tesla MRI systems, they were able to image lesions within epileptic patients' brains that were essentially invisible in the 1.5 Tesla or 3 Tesla imaging systems. And so you can imagine that the 7 Tesla MRI systems would have a huge impact in clinical applications. However, currently they're being limited because of the fact that the radiofrequency coils within these systems are still designed and rely upon the parameters for the traditional 3 and 1.5 Tesla systems. So they're not optimized in terms of the signal to noise ratio that they're receiving. They're not optimized in terms of the energy deposition that they would be depositing into the tissue of the patient. And so to deal with that, what we're doing in this paper, which is still relatively in its infancy, is combining different ideas from previous works that we've done. In a previous study, this group has found that if you were to achieve the ultimate intrinsic SNR for a array configuration, you would need to combine both loop elements as well as dipole elements inside the RF coils. And a different work has found that you can actually analytically model the electromagnetic interactions and figure out how to calculate the electric or resistive coupling coefficient as well as the inductive coefficient between two array elements. And save time because the traditional or conventional MRI electromagnetic solvers take a lot more take a lot more time and computational resources to accomplish that. And so in this paper, we utilize that analytical model with these two rectangular coils that you can see in Figure 1, kind of along a cylindrical phantom, and vary the actual width for these two array elements, as well as the overall distance that they're placed from the cylindrical phantom. And so using the optimization toolbox in MATLAB and a script that essentially uses the dyadic Green's functions outlined more in depth in other works of literature, we find the electric coupling as well as the magnetic coupling coefficients and plot them for kind of a parameter sweep in both the distance that the coils are placed from the phantom as well as their initial width for those coil elements. And so what we found currently is that there seems to be two kind of at the extremes for the initial width. If the width is too tiny or if the width is too big, you end up having really erratic behavior for both the coupling coefficients as well as the optimum width and overlap signified by alpha for these array elements. However, we were able to find that there are regions between these kind of erratic behavior zones where the behavior is a lot more systematic and linear. And so this will inform our design moving forward, where we are going to use commercial full-wave electromagnetic solvers to verify a couple of designs that are more easier to manufacture, and then go ahead and actually design those and physically test those designs to experimentally verify that our loop and dipole array minimizes the electric and magnetic crosstalk between different array elements and is able to optimize the SNR and achieve something closer to the ultimate intrinsic SNR. And so with that, we'll then be able to move one step closer into bringing the 7 Tesla MRI systems into clinical practice and opening up a lot more avenues for what we're able to image and what we're able to detect for different patients. Thank you for your time.